Okay, so we have two lead bricks moving toward each other. Each have kinetic energy K. They crash into each other. They come to a stop. What happened to the energy? Let's start at the bottom. Since the blocks were moving in opposite directions, the initial kinetic energy of the system was 0, so there was no change in energy. No, I see a lot of people going, no. Why is that not true? Kinetic energy, you can't have negative kinetic energy, can you? Yeah. So the kinetic energy of the system was positive. What was probably 0 if the blocks had equal masses? Well, each one has a non-zero velocity. But if you took two blocks as the system, they have equal masses, they're moving at equal speeds. What's 0 for the system? The momentum, the total momentum of the system might have been 0. But kinetic energy is a scalar, and it's always positive, so the system did not have 0 energy to start with. Okay, nobody, I think, liked having the total energy of the system decrease because something had to happen to the energy, right? It can't just disappear. Kinetic energy, the most popular answer was kinetic energy changed into thermal energy. That makes sense because if you think about this lead block as being this mass of balls and springs, little atoms connected by bonds, what happens to the energy when they smash into each other? All those little things just start vibrating more, don't they? And that's what we mean by thermal energy. Lots more action at the microscopic level. If you measured the temperature of the blocks, would have gone up, right? Now, the kinetic energy changed into rest energy. Well, it depends on how you meant that. The internal energy of the block went up. And since there is an equivalence between energy and mass, if you took this hotter block and you very, very carefully determined its mass, it would be slightly more massive because of all this internal energy. It's not something that would be easy to measure. It's a very small amount. So remember we talked about the energy of a multi-particle system, mass energy equivalence. So yes, but if that's not what you meant, then maybe not. Okay. So we've been talking, this is an example of energy dissipation. What we mean by dissipation is that kinetic energy is often in something that could be useful. We could take the kinetic energy of a moving block and have it hit something and turn a wheel or something, so we can use it to do something useful. Once energy, that kind of organized energy, goes into this very disorganized thermal motion, it's hard to get it back and do anything useful with it, so people often say it's been dissipated. It hasn't been lost, it's just been converted into random motion of lots of little particles, and it's sort of hard to get all that back to make the block. Once you have a hot block sitting here, it's very unlikely that all the atoms in the block will then suddenly start moving in that direction at the same time, so the whole block goes off that way. So that's we're sort of edging up to this concept of entropy, which we'll be talking about at the end of the semester. So energy dissipation. And so friction, of course, is another source of energy dissipation. If you slide a block across the table, you just rub your hand on your desk fast, you can feel both your hand and the desk starting to get hot. So all that kinetic energy of your hand is being converted into random thermal motion of the little atoms and chemical bonds in the hand and the desk, and that's another kind of dissipation. Another kind of dissipation is, of course, air resistance. And it's something that we actually do encounter fairly often in in the ordinary world. If you've ever skateboarded or ridden your bike down a hill, you certainly feel that the faster you go, the more the force of the air pushing back on you. That's air resistance, and it matters. More streamlined cars get better mileage because, in fact, the force of the air pushing backwards on them is less. So air resistance is an important thing. In fact, although we like to do problems where we neglect air resistance, and for things moving sort of slowly, that's reasonable, it can be pretty important. So here is a VPython program that's modeling the motion of a baseball or a ball that starts out at about 45 meters per second, which is about 100 miles an hour, both with and without including this air resistance force. Now, the air resistance force, of course, is going to be always in a direction opposite to the motion of an object. So it's going to be in the minus v direction, right? So let's run it with air resistance first, and we're going to show the gravitational force on the ball, the air resistance force, and the net force here, and then watch the path of the ball. So the red force is the gravitational force due to the Earth. The cyan arrow here is air resistance, and notice that air resistance is bigger when the ball is moving faster, and then the magenta arrow was the sum. Okay, so that's the path we predict. Now let's start it with exactly the same initial conditions, but no air resistance. Okay, so the only force on it now is the gravitational force. Look how much farther it goes. It's under these conditions, it's more than a factor of 2. So without air resistance, it would be extremely easy for those major league batters to hit home runs out of the park every time. They could double the distance, couldn't they? When things are moving fast, yeah. So can you do that? So when things are moving really fast, air resistance is a big deal, and when they're moving fairly slowly, it's not. Now, what's going on with air resistance? Let's think for a minute about what's really happening. No, that was not what I meant. That.